Alright, so welcome to a video that I've actually been planning to make for a long time, but I didn't really have the time to, which is this is not going to be a regular series. This is just whenever I have free time to do this. We are going to be doing some past papers of maths, and in this case, further maths, from various countries' syllabuses. Well, various countries' exam systems and exam like secondary school or high school or even college level exams that I can find that are in English. I can find plenty of them that are maybe not in English, but I'm gonna have a pretty hard time finding an English translation of them. So I'm just gonna stick to ones where I can use an English version of the paper, or there is an English version available. If not, then it's going to be kind of a struggle. So we're going to be doing the Pearson Edexcel. So basically, this is the one of the main exam centers, or I guess institutions, if you will, in the UK that handles the GCSE, IGCSE, and GCE papers, which are essentially the standard exams that British students have to take. GCSE being their high school exams, and then GCEs being the exams that they take to get into universities. So basically, we call them college, which is essentially sixth form. So it's the last year of your high school that you take, or college that you take before you enter university, right? So this would be the paper that would have been sat by students in 2020. As you can see, Thursday, 14th May 2020. This would have been sat by students that were taking the further maths subject, because further maths, unlike maths, is an optional elective course for science stream students. You can pick up to 4 or 5 subjects you can take for your GCEs or A levels, further maths being an optional paper. So most science students usually take stuff like chemistry, physics, biology, etc., with maths as a common core. However, there would be students who would take like their fourth subject, which is not required because you have to take a minimum of 3 subjects, but maths is definitely the one compulsory one, with stuff like biology, computer science, psychology, and in this case further mathematics, as being optional subjects that you would take depending on which pathway you would pursue. So if you were like a medical student, for example, you'll be taking biology. If you're a computer science student, you'll be taking computer science. If you're going into something like engineering, physics, or math, you would take further mathematics. Although it is not a requirement in a lot of universities nowadays to have further mathematics, but it's basically a subject that you would take if you are confident enough to basically get an edge in this particular realm. Because further mathematics basically covers stuff that normal mathematics doesn't cover, and to a much more in-depth in-depth level. So the people who will be taking this are people who are going for either a maths degree, or people who just want to be ahead of people who didn't take further mathematics, so that they would have an easier time when they would go to like engineering or physics, where the mathematical background of people who did take further maths would be much more built and like well-rounded compared to people who didn't and have to study all of that from scratch. Is basically they have to use a bit more time to understand these concepts, whereas people who did take the subject would have a more edge. But usually, people just take further mathematics either because they like maths or because they want to challenge themselves, which I did. Luckily, I got an A star, but I didn't take the Edexcel paper, which is what we're going to be doing. I took the regular Cambridge assessed further mathematics paper, which is a slightly different syllabus from Edexcel. Edexcel actually has their syllabus goes into a bit more depth on a lot of topics, and they have way more further mathematics subjects in terms of the amount of topics they cover compared to the regular Cambridge ones. But it's because Edexcel also offers different pathways that you can take in further maths depending on whether or not you want to go into physics or computer science or engineering or maths. Because, for example, if you were going into statistics or analytics, you would take the further stats route. If you went into physics, you would take the further mechanics route. If you went to computer science, you would take the decision maths route. And if you went to just pure math major, you would take the further pure maths route. But this further maths is the common core further maths paper that every student who takes further maths has to sit. It is the AS Advanced Subsidiary paper, meaning it's the first year of A levels, and this is the one that every student has to take because it is part of options A, B, C, and D. Options being, the four routes I just uh, specified as to what kind of maths-based field or like maths-centered field you want to pursue in university. But this is the one that every student must take. So we're going to be trying out this paper today. I think that was a very long introduction as to what this paper is all about in the background. But this is mainly for people who are not familiar with this particular system. This is mainly basically the UK and a lot of other countries, including the country where I'm from, where you can take this as like an option. This is an option that you can take in order to prepare yourself for university, and of course, most universities would accept this particular subject or this particular exam system. So what we're going to do is we're going to try and cover this entire paper. As you can see, this paper is 20 pages, but most of them are just answer spaces. So we're going to try and see. So let's read the rules. You must have mathematical formulae and statistical tables. I don't think I'm going to be needing that since further stats isn't a thing, and I think I have a lot of the formulas down. Calculator, well, I do have a calculator with me, but let's see how much of it I need to use, depending on how much trigonometry there is, or how much quadratic equations are going to be in this paper. So I'm not going to write my name and whatever because, we're not actually taking the exam. Also, I'm not going to give myself a time limit because this video is not meant to challenge myself or doing the paper, but just showcasing the kinds of questions that this further maths paper is going to ask. Right? So this is Further Pure 1. This is the very first Common Core further maths paper that all further maths students need to take. It's the very first one that they sit for. Candidates must use any calculator allowed by personal regulations. I'm pretty sure my one is allowed. Calculators must not have the facility for symbolic algebra manipulation, differentiation, integration, or retrievable mathematical formulas stored in it. AKA, don't try to cheat by typing in derivatives and integrals into your calculator. Instructions: use blacking or ballpoint pen. We're going to use it. I'm using a mouse. The pencil is used in diagrams, sketches. Okay. Fill in the boxes at the top of this page. Nope. Answer all questions. Okay. Answer the questions in the space provided. There may be more space than you need. Yep. You should show sufficient working. We'll check the answers later. Inexact answers should be given to 3 significant figures unless otherwise stated. Information. The booklet. Okay. The total mark for this part of the examination is 40. There are 5 questions, so we might actually have a bit more, bit less. We might actually need less time than we thought. The marks for each question are shown in brackets. Use this as a guide as to how much time to spend on a question. All right. Advise to read each question before you start answering. Try to answer every question. Check your answers if you have time at the end. So this paper is the afternoon paper, meaning this is the paper that people would be sitting after lunch or something. I don't really see the time. It doesn't say how much time this paper is supposed to take. Not that I'm seeing it. So let's just go to page 2, which is essentially the start of the question. So let's start off with question number 1 out of 5, according to them, which is this is basically going to be the first Further Pure Maths paper. Number 1, the variables x and y satisfy the differential equation this, where dy dx is equal to 3 and y equals 0 at x equals 0. Use the approximations of this and this with h equals 0.1 to find an estimate for the value of y at x equals 0.2. So we're trying to find the value of y at x equals 0.2. So if I'm not mistaken, this is essentially the approximation of the solution to a differential equation by Taylor series or Maclaurin series, because we are dealing with it's infinite series centered at 0, meaning that we're going to be dealing with Maclaurin series. Taylor series being ones that are not centered at 0. So the general formula for, I'm not going to really write much on the lines, but let's try. The general formula for Maclaurin series centered at 0 is f of x is equal to, by approximation, we're going to write out the sigma version of this. So it starts from n equals 0 to infinity. And it is the nth derivative of n centered at 0 over n factorial times x to the n. All right, this is the general formula for a Maclaurin series centered, a Taylor series centered to zero of any function, essentially. So what we're trying to solve is we're trying to find the estimate of y at x equals 0.2. So what we want is that we want at least three terms because we do have the d2y dx squared here, so this one's going to be easy to deal with. So let's deal with the first three terms, which are going to be the zero, first, and second derivative. So the zero derivative at 0 is just y of 0. So let's just write out the first three terms that we need. So we want the first derivative, which is basically f of 0 over 0 factorial x of 0, plus f prime of 0 over 1 factorial x1, plus f double prime of 0 over 2 factorial x squared, and then so on. That's what we need. So this is all going to be equal to f of x, right? So we're just going to replace the f of x with y because that's just going to be easier to deal with because we are dealing with y's with respect to x. So f of 0 is simply what is y when x equals 0, y equals 1. And we know that y equals 0, x equals 0, so this entire term is just 0. So the first term is 0, right? Because 0 over 0 factorial is 1 times 1 is just 0. F prime of 0 basically means when x equals 0, dy dx is equal to what? And it's 3. So we have 3 over 1 factorial times x plus, well, to be fair, we are dealing with iteration here. So f double prime of 0 is going to be the one that we want to find. So we want the dy, d2y dx squared, we're just going to rewrite it as the one we want. d2y dx squared centered at 0 over 2 factorial x squared. Right, so that's what we're looking for. So according to this one, what we want here is we want a iterative approximation. So we want an approximation for this one, if I'm not mistaken. So let's denote what y of 0 is first. So I'm assuming this is a approximation by a step function of some sort. Use the approximations this and this with h equals 0.1. Okay, so we're gonna let n equals 1. All right, so let's try this one. So let's let n equals 1. So we're going to substitute it into this formula. So we have dy dx of 1. So basically our first iteration is equal to, not equals, approximately equal to y sub 2 minus y sub 0 over 2 times 0.1 because we want h to be equal to 0.1 is 0.2. So what we want is we want y sub 2. Now we're just going to assume that the first derivative answer we get is the one we want, which is 3, right? Which because it's given here. So y sub 0 is the first y value that we get, so it's going to be 0. I'm assuming. So it's y sub 2 minus 0 over 0.2. So y sub 2 is going to be approximately equal to 0.6, right? Based on our formula. So we're basically doing iterations to find the next gradient for the next y value. Gradient for the next y value. This is kind of like a step function approximation to the derivative. Now the reason we need y sub 2 is because of the d2y dx squared that we need. So from what I'm seeing, we don't need this 0 of 1 because 0 of 1 is just going to be how much the value of d2y dx squared is at x equals 0. Well, actually, that is what we need, though. Hmm. So what we would need then is, okay, we're trying to look for b2 squared of 1, I'm assuming. Because this is an iterative formula. So let's just write out the formula for now. So this is going to be equal to y sub 2 minus 2y sub 1 plus y sub 0 over 0. So it's squared, so it's going to be 0.001. And this is what we're looking for, I think. Or no, we're looking for the initial value. Wait, actually, okay. Let's try and rethink this. Let's say we are looking for the 0th iteration, which is essentially what we're looking for. Let's say we replace this with 0. That means that we are going to end up with y sub 1 and y sub negative 1. Y sub 1 and y sub negative 1. Right? So y sub 1, let's assume, is 0. All right, so let's say the first y value. So y sub 0 will be when x is equal to 0. All right, so let's try. When y is equal to 0, x is equal to 0, so let's sub 0 both into that. So basically, this is, so d2y dx squared is equal to negative 1 when y is equal to 0 and when x is equal to 0. X is equal to 0. Y at x equals 0.2. Hmm. H equals, all right, let's try and sketch a graph. I think what I'm trying to do is, so y equals 0, then x equals 0 is here. Then, okay, I'm going to come back to this question later because I'm not sure what I need to do with this one yet. So let's just, I'm going to come back to this question later. Trust me. We're doing this like a, all right, this one looks way more doable. All right, let's try this one. Use algebra to determine the value of x for which this is true. All right, this one I can deal with because this one is just an rational inequality, which means we're just going to have to do a lot of algebra and factorization. So x plus 1 is over 2x squared plus, oh god, 2x squared plus 5x minus 3 is greater than x over 4x squared minus 1. So if we were to factorize the bottom denominator, we would probably get 2x plus 1, I think, and then x minus, oh wait, it's the other way around. It's 2x minus 1, and then x plus 3, because 2x squared is 6x minus x is 5x, right? That's what we get. And then this was just a difference of 2 squares, so we're going to get 2x plus 1, and then 2x minus 1. Now to solve a rational inequality, you basically have to set one side equal to 0, so we're going to have to move this, we're going to have to subtract this from both sides, so we're going to end up with x plus 1 over all of that minus this right-hand side is greater than 0. Right? So what we can do now is we can combine this into one fraction by multiplying by lowest common denominator. So this one is missing a 2x plus 1 factor. And this one is missing an x plus 3 factor. All over those big boys. And all of these are greater than 0. So what we're going to do is we're going to expand the top and then simplify it. So 2x squared plus 3x plus 1 minus x squared minus 3x over all of that. Apologies for not writing properly on the lines. I would do that if I were actually sitting for this paper, but I am not. So let's simplify the top first, because that's what we need. So we're left with x squared plus 1, which is always positive. Right? So 2x squared minus x squared is x squared. 3x minus 3x is 0, so we're left with x squared plus 1 over all of that. So what this basically is asking for is it's basically asking for the range of values of x such that this inequality is true. Right? We basically manipulated that equality from the top here. Right? So this particular one, because the top is positive, in order for this fraction to be positive, this bottom must also be positive. So we want to determine the values of x for which this denominator is positive. So what we're going to do now is we're going to create a table and basically draw out some critical values. So what I mean draw critical values, we're basically going to set each of these equal to 0 and then find at which points do those happen. So we have negative half. We have, oh wait, negative 3 is actually the far left. Negative 3, negative half, and then a half. What we're going to do now is we're going to then test each of these points. So what we're going to say is test each of these points and basically say, let's test a value that is greater than half, between negative half and half, between negative half and negative 3, and less than negative 3, and see which regions essentially give positive values for this particular denominator. So let's say we test a value between negative half and half, and if that value makes this part positive or makes the denominator positive, then all values within this range are positive, hence we can accept that value. Because if this denominator is positive, the overall fraction is going to be positive, which satisfies the inequality we're going for. So let's test, first of all, a value that's greater than half. So let's just test x equals 1, for instance. So we sub 1 into here, which gives us 2 times 1 minus 1, which 2 times 2 minus 1, which is 1, times 4 times 3, which is greater than 0. Hence, this side is positive, so we're going to have a big plus sign to show that anything greater than half is positive. Because if the easiest one we can find, which is 1, works, then any bigger number is going to work. Anything between negative half and half, well, easiest one we can test is 0. So 0 would give us negative 1, 3, 1, which is always negative, which means that anything between negative half and half is always going to be negative, so we're not going to accept this region. Negative half and negative 3. Let's test negative 1. It seems like the easiest one to test. That's going to give us negative 3, 2, and negative 1. Right? Because if we sum negative 1 into each of these, we're going to get negative 3, 2, and negative 1, which this one is also always positive. So this anything between is always going to be positive because these two numbers, no matter what, are always going to be positive. Always going to be negative. Right? Because if you notice, if these negatives get bigger or get smaller, these negatives are going to get, if the x's get more negative, then these are going to get smaller, which are always going to be negative. Anything less than negative 3, let's test easy negative 4, which is going to be kind of a big number. So it's going to be negative 9 and negative 1 and -7, which is always negative. So this side is always negative. So if you notice, anything less than -3 is always going to make this bottom negative, and it's definitely going to make these others negative. So overall, it's still going to be a negative number. So the only regions that make the denominator positive is this and this. So our answers are going to be those ranges, because this top is always positive no matter what, because x squared plus 1's graph looks like this. No matter what x you plug in, it's going to be positive. So we just care about which values of x make the denominator positive. So the overall fraction is still positive. And we find that the only ranges that make the denominator positive is these particular ranges. So the answer is going to be x must be either between -x and -half, or x must be greater than half. Or if you want to use interval notation, which you can use, you can say it's between -3 and -half, union half to infinity. The reason there are no closed brackets is because there are no equal signs. So we don't include the boundaries themselves, because that's going to make the denominator 0, and we all know that denominator equals 0 equals bad stuff. That bad stuff is going to happen. All right. So this is our answer for question number 2. All right. So let's move on to the next. So these are just exercise. All right. Question 3. Looks like we have somewhat of a Weierstrass substitution. Use the substitution t equals tangent x/2 to prove this thing. All right. Let's try it. I think I'm gonna actually use this. All right, so let's use the other page, because I don't think the first page is gonna have enough space for me to do that. So question 1, we want to prove that cotangent of x plus tangent of x/2 is equal to, what is it again? Cosecant of x. All right. So we can choose to either prove this side or this side. We're going to prove the left side, because the left side makes it a bit more complicated. So if we let t equals the tangent x/2, cotangent of x is simply just 1 over tangent of x. So we just need to find the expression of cotangent x in terms of t. So we know that tangent of x is equal to 2 tangent squared. Oh wait, not 2 tangent squared. 2 tangent of x/2 over 1 minus tangent squared. This is from the double angle formula, or this is the half angle formula in this case. So we can just substitute t into this. So we get 2t over 1 minus t squared as the expression for tangent of x. So cotangent of x is simply going to be equal to the reciprocal of this, 1 minus t squared over 2t. All right, so this means that cotangent of x plus tangent of x over 2 is equal to 1 minus t squared over 2t plus t itself. So we're going to try and combine these into one fraction. So we're going to get us 1 minus t squared plus, well, we just have to multiply this by 2t, so we get 2t squared over 2t. All right, so let's simplify this. We get 1 minus t squared plus 2t squared, which is 1 plus t squared over 2t. Now let's see what we can do. Cosecant of x is just 1 over sine of x. So let's figure out what the sine is for in terms of t. So sine of x is simply equal to 2 times sine of this cosine of this. So we can infer from t being equal to tangent of x over half that if we look at the unit circle, we're assuming here that x over 2 is in the first quadrant. So this is x over 2. So if t is equal to tangent, that means it's t1, opposite over adjacent. So this one's going to be square root of 1 plus t squared. So sine of it is going to be t over the hypotenuse. Cosine is going to be adjacent over the hypotenuse. All right. So that's going to be equal to 2t over 1 plus t squared because the square root becomes square. Now cosecant x is just the inverse of this, or the reciprocal, so it's going to be 1 over this. All right. So since we've proven that these two are equal to the same thing, our conclusion is cotangent x plus tangent x over 2 is equal to cosecant x. All right, that is our solution, and that is the solution to, that is the solution to question number 1. Seems pretty straightforward, so this one's done. X is not equal to n pi, because if x is equal to n pi, then this would be infinity, so we don't want that. Question 2. An engineer models the vertical height above the ground of the tip of one blade of a wind turbine, shown in figure 1. The ground is assumed to be horizontal, right? The vertical height of the tip of the blade after the ground, h meters at time x seconds after the wind turbine has reached its constant operating speed, is modeled by the equation this. Show that h equals 60 when x equals 0. All right, so let's try that. So let's see, do we have space for this one? Let's just use a new page. All right, so we're going to use this for question 2. So part A asks us to show that h equals 60 when x equals 0. So let's copy down what h is. H is equal to 90 minus 30 cosine of 120x in degrees minus 40 sine of the same thing. All right, that's what we want. So we're just saying when x equals 0, h is equal to 90 minus 30. Cosine of 0 is 1. All right, minus 40 sine of x, sine of 0 is 0, so this is equal to 60. Shown. All right, pretty easy. Just substitute values and just know what you're doing. All right, that's pretty easy. Pretty easy 1 mark. Question B. Using the substitution, tangent t equals to tangent 60x, show that the equation 1 can be rewritten as follows. All right, now B basically says t is tangent 60x, which is essentially half of the internal degrees. Now, this is essentially just cosine double. So let's see, cosine of 120 degrees. All right, so let's just write out the relevant corollaries that we get, basically the relevant numbers from the previous ones. So we already know what the sine one is going to be, because that's what we got. Sine of 120 degrees x is equal to 2t over 1 plus t squared. Cosine we're just going to have to prove separately, but it's not that difficult to prove. It's simply going to be, let's see what we can use. Let's use one of them. Let's use the cosine. That's going to be much easier. 2 cosine squared of 60 degrees x minus 1. So this one is going to be equal to 2 times 1 over 1 plus t squared, because it's after it's squared, minus 1. So it's going to be 2 over 1 plus t squared minus 1. If we combine denominators, we're going to get 1 minus t squared over 1 plus t squared. We just make this the common denominator. So 1 plus t squared on top, 1 plus t squared on the bottom. So it's 2 minus, all right, so I'm just going to bracket this just for your sake. This is 2 minus 1 plus t squared, which will give us that. All right. So that's cosine. So let's replace h with all of them. So h is equal to 90 minus 30 of 1 minus t squared over 1 plus t squared minus 40 of the other one. All right, so let's combine these all into one denominator. 90 bracket this minus 30 bracket this minus 40 bracket this. all over 1 plus t squared. Oh, t squared. Right, so this one is going to be equal to, let's simplify, 90t squared plus 30t squared is going to be 120t squared minus 80t, and then the numbers are going to be 90 minus 30, which is plus 60 over 1 plus t squared. Is that what they want? Yep. So this is shown. Right. And then the final part, I think, is part C. Yep. Hence, find, according to the model, the value of x when the tip of the blade is 100 meters above the ground for the first time. So what we want is to find the value for which h is equal to 100. 100. So this is just going to be solving a quadratic equation. So let's simplify this down a bit. All right, so solving our quadratic equation should be a problem. Let's watch our space. Is the next one the next question already? Nope, we still have space. Good. You know what? Maybe I'll actually, maybe I'll do this on the next page. Cut, paste. Let's do that here because this is going to be much easier for us to deal with. Let's do it here. All right. So this is going to be 100 plus 100 squared, multiplying both sides by the denominator. It's equal to this. So we rearrange some things. This is going to be 20t squared minus 80t, and this on the left side will be minus 40. Divide everything by 20 because that's just a constant. We get t squared minus 4t minus 2 is equal to 0. This is what we get. All right. Now, this one is going to be, this one can't be factorized, so we're just going to use the quadratic formula here. T is equal to 4 plus minus 16 minus 4ac, so 2 over 2. So this is going to be plus 8, so square root of 24. Square root of 24 is 2 root 6 over 2, which is equal to 2 plus minus square root 6. Now, 2 minus square root 6 is going to be negative, so we want, because t is time, we're going to reject 2 minus square root 6, hence t is equal to 2 plus square root 6. But they don't want the value of t, they want the value of x, I think? Yep. 100 meters above the ground for the first time. So, all right. All right, so value of x when the tip of the blade is 100 meters above the ground first time. So this one is going to be t tangent 60 x degrees, because that's what t stands for, is equal to 2 plus square root 6. 60 x degrees is equal to tangent inverse of this. So this one's going to need our calculator. Hence why calculators are needed, because this question exists. So tangent, hence this why this paper needs a calculator. We're going to write 4 decimal places just to be safe first. 77.3335 degrees. 60x degrees. So x is going to be equal to this divided by 60, which to 3 decimal places, to 3. Wait, what did the paper request? 3 significant figures. So we're just going to give it a 3SF. It's going to be 1.29. X is in seconds. Okay? Yep, x is in seconds. So 1.29 seconds is the first time that it reaches 100 meters. Right? So that is the entirety of question 3. Let's move on to question Oh, more space. 4. So it looks like a conic section question, so this is going to be fun. All right. Figure 2 shows a sketch of a parabola C with equation y squared equals 4x, right? Point CS is the focus with point P, right? Write down the coordinates of S. So this is essentially just testing you if you know how to write the focus of a parabola. So focus of a parabola is just, this is going to be y equals 0, but it's going to be, this is going to be 4 times ax. So yeah, so it's just going to be a comma 0, because that a is basically the distance of the focus from the origin, or from the vertex, essentially. From the vertex, right? So it's a units away from the vertex. So that's the coordinate of the focus. B, write down the length of SP in terms of A and P. So we're just going to find the distance. SP is equal to square root. So we're going to have this to this. So AP squared minus A squared plus 2AP squared, because it's minus 0. So let's try and simplify this. We're going to get A squared, because we're factorizing A out, P squared minus 1 squared plus 4A squared P squared, which is going to give us, let's factorize A squared out of both of them. So we're going to get A square root P to the 4th minus 2P squared plus 1 plus 4P squared. A bracket square root P to the 4th plus 2P squared plus 1, which is essentially just a P squared plus 1 squared. So it's a P squared plus 1. All that with 1 mark, right? A P squared plus 1. All right, let's look at question C. The point Q, where P is not equal to Q, also lies in C. The point M is the midpoint of PQ, given that PQ is equal to minus 1. Prove that as P varies, the locus of M has the equation. All right, so let's try and rewrite this. So C. So P has this coordinate, has these coordinates, which are basically just parametric coordinates for parabola. Q has these two. And the locus of M is the midpoint of P and Q. So mid M is equal to, let's double check, is, yeah, midpoint. So it's this plus this over this, and then this plus this over this. So this one, the summary is equal to A P squared plus Q squared all over 2, comma, AP plus AQ. All right, so we want to find the locus of the locus of M, how M changes with P and Q, has this particular equation. So let's see. So X in this case is equal to this, and Y is equal to this, A bracket P plus Q. So let's say we want to find, let's say we substitute A for something. So A, in this case, is going to be equal to Y over P plus Q. So let's say we call this equation 1, 2. So we sub 2 into 1. So we're going to get is X is equal to Y over P. All right, let's just move the 2X to, let's just move the 2 up, multiply both sides by 2. 2X is equal to Y over P plus Q times P squared plus Q squared. Plus Q squared. Okay, hold on. What does it say in the question again? Okay, hold on. It says prove that as p varies, the locus. All right, pq is equal to -1. Okay, so we don't want a to be gone. Oh, okay, hold on. So we can rewrite x as a over 2 times p plus q squared minus 2pq. Because if you expand this out, this is going to be p squared plus 2pq plus q squared. The 2pq's are going to cancel out and be left with this. So we can rewrite this as this. All we also know is that p plus q is equal to y over a. So we can say this, set this as 1 and set this as 2. And we say sub 1 into 2. So we're going to get that x is equal to a over 2 bracket. P plus q is just y over a, so we get y over a squared. And we know that pq is equal to -1, so this is going to be plus 2. Right, so let's simplify that. A over 2 y squared over a squared plus 2. So let's expand this. We're going to get y squared over 2a, because these two a's cancel out. And then this is going to be just a. So let's multiply both sides by 2a. So we're going to get 2ax is equal to y squared plus 2a squared. Hence, y squared is going to be equal to 2ax minus 2a squared. Or, what does it want? It wants 2a bracket x. 2a x minus a. So this is what it requires. So this is shown or proven. Alright, so that is the solution to question C. Alright, next question. Do we have more space? Probably more space. Yep, more space. Question 5. This is the last question, and then we have to go back to 1 because we haven't finished that one yet. This looks like a vector question. Figure 3 shows a solid display stand with parallel triangular faces. Alright. Similar, meaning that the angles are going to be all the same. So, for example, similar just means that, for example, this angle and this angle are going to be the same. With respect to a fixed origin O, the points A, B, and C have, let's just label that. Okay, it's much easier to see when you just label the pictures like that. Alright. Units are in centimeters. Alright. Show that the area of the triangular face DEF is that. Alright. So let's just try to rederive the formula for the area of a triangle. So the area of anything is half AB sine C. A and B being this length and sine C being this angle right here. So it's angle EDF. So we can say that this is going to be equal to half the magnitude of vector DE, magnitude of vector DF, times the sine of the angle EDF. So essentially just the angle between DE and DF. But if you realize this is just the definition of the cross product, right? DE cross DF. This is from the definition of the cross product, which says that A cross B is equal to magnitude A, magnitude B, sine theta, where theta is between A and B and then some unit vector, but the unit vector doesn't really matter. All right, this is from the formula of the cross product, which is just magnitude B, sine theta, which is theta was between A and B. All right, so we just have to find the magnitude of dE cross dF. So first off, we actually have to find dE and dF first. So let's write dE and dF down. dE is equal to OE minus OD. So we're going to use column vector notation. So E is this minus OD, which is this. So dE is equal to negative 4, 3, 1. All right. dF is equal to OF minus OD. So OF is this minus this. So this is equal to negative 1 by 2. So dE cross dF is equal to negative 4, 3, 1 cross negative 1, 5, 2. So we're going to use the general cross product notation. All right, so we're going to have to solve this with a cross product. So this is going to be equal to 6 minus 5. So it's going to be 1. Negative 8 plus 1, negative 7, positive 7. Negative 20. All right, so I'm just going to write out what we're doing. It's 3 times 2 minus 1 times 5. And then negative of negative 8 plus 1. So 1, wait. Yeah, negative 8 plus 1. So negative 1 plus 4 times 2. And then finally we have negative 4 times 5 plus 3 times 1. So this is equal to 1, 7, negative 20 plus 3, negative 17. Right, so we're going to have to consider this as a separate page because this one is actually quite long. So, the magnitude of this cross product, recall back to the previous, is so let's see. So we're going to use calculator to solve this because it'll save time. Square root of 339. So the area of dF is equal to half square root 339 units squared. Yep, oh, cm squared, right? It's centimeters. So centimeters squared shown. Right, so that's part A. That's a pretty long part A, actually. All right, part B. Find in cm cubed the exact volume of the display stand. Okay. So this is going to be this is going to be base area times height. So base area we can find. Base area is just AB cross AC, and then do that up again. So the height so sine of theta well, okay, not sine, cosine. is equal to height over magnitude of AB. H is cos theta. Oh, okay. So let's write that into our actual working. Okay, so part B. So we want the area of the volume. So we want the volume. So volume is going to be equal to, this is just base area times height. So base area times height. So this is equal to half of the cross product of DE, no, not DE, cross product of the base area, which is AB cross AC. B cross AC, and then the height is going to be cross with a D times the height. So let's just rewrite what the height means. So from our little discussion over here, we found that cosine of theta, where theta is the angle between the height and AD, all right, let's write a D better, AD. So H is actually equal to magnitude of AD cosine theta. All right, so this is equal to half of the magnitude of AB cross AD, AC, times AD cosine theta. Right, where theta is the angle between AD and height. So what we can do is we can use the definition of the dot product to say that if we have two vectors multiplied together and they have a cosine theta, we can just call them the dot product. So it's the magnitude now of AB cross AC and then dotted with AD. Right, so that is the formula of the volume of the entire shape. So first off, we need to find what AB cross AC and what AD are. So let's quickly find out what AB, AC, and AD are. This, sorry for being a bit quiet. I'm just doing a lot of mental math right now. Okay, so that's the vectors of AB, AC, and AD. All you have to do is just take the front minus the back. That's it. So first off, we have to find out what AB cross AC are equal to. That's going to be, let's draw out that determinant table again. So AB is this, and then AC is going to be this. So this one is going to be equal to, let's just write the vector here. 24 minus 20, that's 4. Negative 32 minus negative 4 plus 4, 28, because it's negative. Negative 80 plus 12 is going to be negative 68. So AB cross AC, then dotted with 80, is just going to be this vector dotted with this vector. So negative 4 plus 28 minus 7 times 68, which is equal to, I'm too lazy to count this, negative 452. So the magnitude of this is just going to be 452. So the volume is just going to be equal to half times magnitude negative 452, which is 226 centimeters cubed. That is the volume of this giant shape. All right, and I'm assuming the last 2 pages are just additional space. Yep, it's just additional space. All right, so we have 3 pages of additional space. Okay, so that is the last part of question 5. So now let's go back to question 1 and see how we deal with this again. All right, because we're done with 2, 3, 4, and 5. We're left with question number 1 to deal with. Let's think about this one. Okay, so let's rethink this because if they gave me approximations for these, I'm assuming I don't actually need to use the Maclaurin series formula because if that's the case, that would be a completely different method, and I wouldn't even need to use this method in the first place, right? Because if they gave me approximation formulas for these two, I probably wouldn't need to look for the Maclaurin series expansion of that. Okay, I think I understand. So h is essentially the step function. It's basically the amount of height you increase your x by. So basically your n will go from x to x plus h to x plus 2h and so on, right? That's how your approximation works. So y sub 0 would start at 0, y sub 1 would go to 0.1, and y sub 2 would go to 0.2. So that's what the step function is, right? So the h basically amounts to the amount of increment you increase your x by. So y sub 0 is just 0, right? Because y sub 0 is the first 0 we encounter. Y sub 1 is going to be y when x is equal to 0.1, right? So we know that dy dx of 0, which is the starting one, is equal to 3, right? Because this is when x is equal to 0, y equals to 0. Y at 0.2 is just going to be, we need to find what y sub 2 is equal to. We basically need to find what y sub 2 is. All right, so let's list down all the information we know written in this notation. So y sub 0 is just going to be our starting point, which is 0. Yeah, that's what it is. I think that's all the information we have here. So let's try and figure out how we can determine what it is. So dy dx of 1 is basically going to be what y is equal to at 0.1. So, okay, if we can actually infer what d2y dx squared of 0 is, because d2y dx squared of 0 is basically when x is equal to 0. Right, so when x is equal to 0, y is equal to 0. So we're going to get negative 1. That's what we infer, because that's going to be 2 times 0 minus 1, which is just negative 1. So we have an extra piece of information right here from the differential equation. So these are our three starting values. And what we want to get to is, if our step function is h equals 0.1, we have to take 2 steps, aka get to n equals 2 to achieve x equals 0.2. So our goal is y sub 2 is equal to 1. All right, so basically, to explain how iteration for this works is that this h basically amounts to how much our x increases by as we try to approximate different values. Right, so if we want to find the value of y at x equals 0.2, if we use h equals 0.1, we're basically increasing x by 0.1 each time we iterate, or each time we try to calculate a new value. So x equals 0.2 is basically going to be the second step, right? It's basically going to be the second value of third value. If we're counting 0 as the first value, then it's going to be a third value of y. We want the third value of y, or y sub 2. So what we can say for certain is that based on this equation, based on the differential equation we're given, the third step, y sub 2, can be obtained with this formula. d2y dx squared, d2y dx squared at the n equals 2, or at x equals 0.2, is 2 y sub 2 squared minus 0.2 minus 1. Right? So in order to obtain y sub 2, we need to find what d2y dx squared of 2 is equal to. All right, so let's try and figure out how we're going to get to d2y dx squared of 2. So what we can try and start with, actually, we don't even need that, because if my hunch is, oh, no, we have to do this. We have to do that. Sorry. Let's try and see how we can approach this. Let's try and see what happens when we plug in n equals 1. So if we plug in n equals 1, we get dy dx n equals 1, which is basically when x is equal to 0.1, is approximately equal to y sub 2 minus y sub 0 over 0.2, right? Which is equal to y sub 2 minus 0, because y sub 0 is 0, over 0.2. Whereas d2y dx squared at 1 is y sub 2 minus 2y sub 1 plus y sub 0 over 0.01, which is equal to y sub 2 minus 2 y sub 1 over 0.01. So, how do we use this to find y sub 2? Well, for starters, we need to know what y sub 1 is, otherwise we can't do anything. And we also need to know the value of these two. Because if we know, well, actually, okay, actually, we could try this one, because this one doesn't seem like it's going to get us anywhere. So let's change up a bit and try the 0th one, because the 0th one actually might get us somewhere. So dy dx of 0 is equal to y sub 1 plus minus y sub negative 1 over 0.2. Now you might be thinking, what the hell was y sub negative 1 going to help us with? Well, you can see. Well, you'll see. If we put dy dx of 0 now, we're going to get 0 equals y sub 1 minus 2y sub 0 plus y sub negative 1 over 0.01. Right? Now we can rewrite these two equations in terms of what we get, because dy dx of 0 we know is 3. So it's 0.6 is equal to y sub 1 minus y sub negative 1. And we know y sub 0 is 0, so we don't have to worry about that. Dy dx of 0 is negative 1. So we're going to say that negative 1, this replaces negative 1. Multiply this over, we're going to get negative 0.01 is equal to y sub 1 plus y sub negative 1. Right? So if we want to find out what y sub 1 is, we just have to say we add these two together. 2y sub 1 is equal to, this plus this is just 0.6 minus 0.01, which is 0.59. Right? So y sub 1 is going to be equal to 0.59 divided by 2, which is 0.295. We're going to keep it that way. 0.295. That's y sub 1. So this is when y sub, right? So this is basically when x equals 1. Sorry, when x is equal to 0.1, y is equal to what? So we can use this, in fact, to determine what d2y dx squared at 1 is equal to, at x equals 0.1 is equal to, because now we also have the differential equation to use. So 2y squared, y at 0.1 is this. The x is simply going to be the x value we're dealing with, which is x equals 0.1 minus 1. All right, so at x equals 0.1, which is what this means, the second derivative of y is going to be equal to that's a long number, but we're going to keep it as long as it is because we're going to keep the answer as accurate as possible. Right, so that is the second derivative. The second derivative with respect to x is 0.1. What else can we do with this one? Oh yeah, now we can actually determine what y sub 2 is. Why? Because from our formula, we know that d2y dx squared of 2, well, 1 actually, 1 is equal to, from the formula of the estimation, is y sub 2 minus 2y sub 1 plus y sub 0 over 0.01. Right? This is based on this formula right here. Right? So we also know from the differential equation what this is. So we can replace this with that value. Right? Y sub 2 is what we're looking for, so we can keep that blank. Y sub 0 is 0, so that they care about that. Y sub 1 we just found is this, well, 2y sub 1 is just 0.59, so we're going to keep it 0.59 equals 0.01. So hence, we determine that y sub 2 is equal to this times this plus this. So roughly equal to, so I'm not going to put equals, we can say roughly equal to, in three significant figures, 0.581. So we actually didn't even need this one, because all we needed was this particular information. So let's copy all this and move up. Yep. So to summarize what we did, for people who are still be confused, we simply let n equals 0 be our starting values, which is when x equals to 0, y dy dx and d2y dx squared are equal to what? So we obtained these two from the information they gave for when x equals to 0, what y and dy dx are. We obtained the d2y dx squared value by substituting x equals 0 and y equals 0 into it, because when x is equal to 0, y is equal to 0, to obtain this initial value. We then use the approximation formulas they give to give an expression for y sub 1 and y sub negative 1 in terms of the values that we obtain, and then added these two equations together. Right? I'm just going to box these two up just to highlight. Box these two up and then add them together to get 2 y sub 1 is equal to this, to find out y sub 1, which is essentially y sub 1 is the n equals 1, which is this first step, which is when x is equal to 0.1, y is equal to what? We can then use that to determine what d2y dx squared is by substituting x equals 0.1 and y equal to whatever y sub 1 is, to get what the value of the second derivative at x equals 0.1 is. And we also know that there is the approximation formula for the second derivative is given by this, by substituting n equals 1 into all of them. We know what this value is from here. We don't know what this is, but this is what we're looking for, because y sub 2 is what y is at x equals 0.2. Y sub 1 we just found. Y sub 0 is just 0. So we substitute all the values in, and then we obtain y sub 2, which is basically what y at x equals 0.2 is. And that is all of the entirety of the first paper of Further Pure Mathematics 1 by Edexcel for the May 2020 paper, or May-June 2020 paper. All right. Hopefully that was slightly easy to understand. I don't know how much of that was easy to understand based on the steps that I laid out, but hopefully you found this a bit entertaining. I will be making a separate video, which I will find time to record, where I go through my answers, where I basically go through uh, this paper right here, and I basically figure out, basically check my answers to see how much I got right and how much I got wrong. And knowing me, I'll probably make some dumb, careless mistake, but given that a lot of these are basically just proof questions, it's not that hard. It's not that bad. Knowing that a lot of these are proof questions, they're pretty fine. So hopefully you enjoyed this little video that I made. And yeah, I'll post the answers video on a separate date, but yeah, I'll see you guys next time whenever I make another video like this, or hopefully suggest to me what kinds of papers you want me to try maybe doing in this kind of style, and suggest to me what countries' papers you want me to tackle that are basically math related. Just make sure it's math. I'm not going to do physics, chem, or biology, just math, because I love math. So yeah, thanks for watching, and I'll see you in the next video. Bye bye.